The topic for today's discussion is electric potential energy of a system of charges. What is it? It is equal to the work done by an external agent in order to bring the charges one by one from infinite separation to the desired position to form the system. Now, let us suppose there are two charges Q1 and Q2. Q1 and Q2, right? At points A and B. At points A and B. Okay, and the distance between these 2 points is r. The distance between these 2 points is r. Now we need to find out the potential energy of this system, right? Okay, initially we will assume that only this charge was present. Q1 was present at point A and Q2 was not present. It was at an infinite distance. Q2 was an infinite distance. Now, the potential at B due to charge Q1, we will assume that Q2 is not present here. Okay. So, we will find out the potential at B due to this charge Q1. Potential at B due to charge Q1. Potential at B due to Q1. Potential at B due to Q1 की हमें 1/4 pi epsilon into Q1 by R into Q1 by R. কালকে derive করেছিলাম এই ফর্মুলাটা। Okay. Now to bring the charge Q2 from infinity, now to bring this charge Q2 which was at infinity to this point P, right? We have to do some work. We have to do some work. Let that work be W. The potential at V due to Q1, let this be represented by V1. And now W, the work done in bringing this Q2 charge from infinity to this point B is V into V1 into Q2. Yesterday or in earlier class, we just did this thing. Work done is potential into charge. Work done is potential into charge. Okay. So this work now gets stored in the system of charges Q1 and Q2 and is known as the potential energy. So what is the potential energy? It is 1/4 pi epsilon Q1 Q2 by R. Q1 Q2 by R. If you remember, very one important thing that I must tell here is, if you remember this thing, that force between two charges F was given as 1/4 pi epsilon. F was given as 1/4 pi epsilon Q1 Q2 by R square, right? Q1 Q2 by R square. And what is the formula for work done? Work done is force into displacement. Force into displacement. So displacement between 2 points is the distance between 2 points. So F dot into S, which is here as F into R. So see, you will get the same formula. You will get the same formula if you multiply F dot R. If you multiply it by R, so R get cancelled and you will get only 1/4 pi epsilon 0 Q1 Q2 by R. Understood? The next topic of discussion: work done in deflecting a dipole in a uniform electric field and potential energy of the dipole. So let us consider an electric dipole. This one at point A and B is an electric dipole, right? Which is placed at an angle theta with a uniform electric field of strength E. This E is the electric field strength of an electric field. Now the dipole moment of the electric dipole is, we know, given by P, moment of the electric dipole, and torque, we have found out also the torque in previous classes. Torque is given as PE sin theta. We have derived this equation. How? You can consult previous classes. Torque is equal to PE sin theta. Now the torque on the dipole brings it along the direction of the electric field. Now this torque will try to bring this dipole along this electric along this electric field. Understood? This torque will try to bring this dipole along this electric field. Now, so when theta becomes 0, when this dipole is in the same direction as the electric field, for example, if I draw, it will look like this, that the dipole is also in this direction. Okay. So now to deflect it, this is the equilibrium position of the dipole. This is the equilibrium position of the dipole. Now to deflect it from its equilibrium position, work has to be done on the dipole. Now if we want to deflect this dipole from its equilibrium position, you have to do some work. And this work is stored in the form of potential energy in the dipole. So let us assume that the initially dipole is in equilibrium position and external torque acts on it and deflects it through the angle theta. Right? Deflects it through the angle theta. In this position, the magnitude of the torque we have found out in previous classes, Pe sine theta. Now, work done by an external agent to deflect it from angle theta to d theta. Now, we will just assume that this dipole will slightly be deflected like this from theta to theta plus d theta to theta plus d theta. This is the very small angle d theta. By this very small angle d theta, it has to be deflected. Now, what will be the amount of work done? Let the amount of work done be dw, and that this will be equal to, work done is always torque into angular displacement. Angular displacement is d theta here. So as linear work done was force into displacement, this angular work done will be torque into angular displacement. Okay. Now total work done will be integration of dw from 0 to theta. Integration of dw from 0 to theta, and this will be equal to t integration 0 to theta d theta, and this will be equal to, sorry, my mistake, t will not come outside, t will not come outside, t is dependent, t will not come outside. Integration e dot theta from 0 to theta, and this will be equal to integration 0 to theta. Instead of t we will write e sine theta d theta, and if you do the integration, e becomes constant, uh, e integration 0 to theta sine theta d theta sine theta d theta, and this will give you integration of sine theta d theta will give you 1 minus cos theta, e 1 minus cos theta. So this is the potential energy in this position. If I remove the red one, if I remove the red one, so in this position the potential energy u of the system, dipole system, is given by Pe 1 minus cos theta. Okay. Now our next topic of discussion is kinetic energy of a charged body in an electric field. Suppose a particle of charge q is moving from one point to another in an electric field. একটা electric field আছে যেখানে একটা charge move করছে from one point to another point. Now, if the potential difference between the 2 points is v, if the potential difference between the 2 points is v, then what happens? The particle loses potential energy amount potential energy of amount qv. It loses a potential energy of amount qv. qv আমরা বলেছিলাম না, work done, it is the amount of work done. So work done has been changed into potential energy. So if the system is itself doing work, then its potential energy will be lost, and the amount of potential energy that will be lost will be equal to q into v, and this will be equal to the kinetic energy of the system. This will be converted into the kinetic energy of the system. Now, if m be the mass of the particle and v1, v2 be its velocity at first and second point. Suppose you have a point here and a point here, and the velocity at this point is v1 and the potential velocity at this point is v2, right? And the potential velocity at this point is v2. So what is the kinetic energy? What will be the kinetic energy? Kinetic energy will be 0.5 m v2 square minus v1 square. Okay, this will be the kinetic energy of the body, and this will be equal to q into v. This will be equal to q into v. Okay, so v is the potential, mind it, capital V is the potential, v1 and v2, let me write them with small letters so that you can understand it is velocity. v1 and v2 as velocity and capital V is potential. Okay, so from this you can easily find out, v1 and v2, you can easily find out. And if the body if v1 is equal to 0, suppose if v1 is equal to 0, then what happens? Then it happens that 0.5 m v square is equal to q into capital V. From here you can easily find out v. Small v is equal to 2 into q into v divided by m whole to the power half. Whole to the power half. Have you understood this?
Yes, sir.